Hi guys, today we're going to talk about atomic theory and the history of the atom and what we think is inside of atoms. Atoms are submicroscopic, they're super small, we can't even see them with a microscope, and so we try our best, and the theory keeps developing up till now of new things that we learn all the time, again because we can't actually see them. So the first people that kind of said everything is made up of certain elements were the Greeks, and this was, 5th century BC, and they basically said everything is made up of 4 elements, but those were different elements than the ones we know now. So they said everything is made up of fire, water, wind, and earth. Then came Democritus. Here's a picture of him. And we say that Democritus is the founder of atomism. He believed that atoms are indivisible and indestructible. Indivisible means they can't be broken down, so they're not made up of any smaller particles, and they're indestructible, you cannot destroy them. The Greek word atomus means uncut or indivisible. Of course, now we know that atoms are made up of smaller particles, subatomic particles, but Democritus said things are made up of atoms, whatever those things are, and that they are indivisible and indestructible. And then Aristotle and Plato, so still, people who were not doing actual scientific research. They were philosophers. They just kind of sat there and thought about, I wonder what things are made of. They said that matter was continuous and can be broken down into atoms. So it's made up of atoms. These atoms are next to each other. So the reason why I can see this table is because it's made up of many, many atoms, and they are continuous. The definition of atom is that it's the smallest particle of an element that retains its chemical identity. And we have that definition in, chapter 2. So for 2,000 years, again, there was no experimentation. It was all philosophers that were, sitting there pondering, I wonder what things are made of, until John Dalton. So John Dalton was an English school teacher. He didn't teach English. He was from England, and he was a school teacher. And he completed his work in the early 19th century, 1803 to 1807, and he presented an atomic theory. And Dalton's atomic theory is amazing because at the time, they did not have a lot of equipment. They were not able to observe a lot of things, and yet most of the statements in his theory are correct until today. There are only 2 words that we disagree with today. So Dalton's atomic theory is 4 statements. So the first statement says all elements are composed of submicroscopic indivisible particles called atoms. So everything is made up of atoms. These atoms are very, very small. So they're submicroscopic. We can't even see them with a microscope. And they're indivisible. They cannot be broken down. His second statement says atoms of the same element are identical. The atoms of any one element are different from those of any other element. So a carbon atom looks exactly the same as another carbon atom, which is exactly the same as another carbon atom. So all carbon atoms are identical. They're exactly the same. But carbon atoms are different from oxygen atoms, which are different from neon atoms, and so on. So atoms of different elements are indeed different. His third statement says that atoms of different elements can physically mix together to form a mixture, or they can chemically combine with one another in simple whole number ratios to form compounds. So we kind of studied this in chapter 2. We said that if we have different elements, we can combine them physically. So for example, air, we have nitrogen, we have oxygen, they mix together in a physical mixture. We can also combine elements to make a compound chemically. So we can take hydrogen and oxygen gases, make a reaction, and form water, for example. So they can chemically combine to form compounds, and when they do that, there's simple whole number ratios like, water is H2O, so it's a 2-to-1 ratio. Or they can physically mix to form a mixture. And then his last statement here says that chemical reactions occur when atoms are separated, joined, or rearranged. However, atoms of one element are never changed into atoms of another element as a result of a chemical reaction. So basically, when I take hydrogen and oxygen gases, I'm breaking the bond between the H2, the bond between the O2, forming a new bond between the O and the H to form water. And so these chemical reactions happen when the bonds are broken, formed, or rearranged. But we can never, with a chemical reaction, change one atom into another atom. So with a chemical reaction, I can't take hydrogen and change it into carbon, for example. I can do that with a nuclear reaction, but not with a chemical reaction. So all 4 of these statements are true to today, except for 2 words. There are just 2 words that we don't agree with anymore. Can you tell which words? One of them is indivisible. So we know that atoms are divisible. Atoms are made up of subatomic particles, protons, neutrons, and electrons, and then protons and neutrons are made up of quarks. They are divisible. We can break them down into smaller particles. The other word that we disagree with is identical. So atoms of the same element are not necessarily identical. Remember, there are isotopes. So there's carbon-12, there's carbon-14, there's carbon-13, and so those have different number of neutrons, and so they're not really identical. So those are the 2 words that we disagree with, indivisible and identical. So on the test, I could ask you to list the 4 statements of Dalton's atomic theory, or a couple of them, or something like that. You don't have to memorize them word by word, but you have to say what they're saying. So same meaning, you can use different words though. Or I could ask you, which parts of Dalton's atomic theory do we disagree with now? You would tell me the indivisible and the identical, and you'd explain why. So basically, if you take 2 pieces of tape, so I'm going to take some tape here, and I'm going to take 2 pieces of tape, and I'll put them on my table here. So I'll stick this one like this, and another one on top of it. And you see that they attract each other. And this is not the sticky side that they're attracting each other, right? And so what does that mean? Well, people noticed that we have this static stuff where things kind of stick together or repel from each other. And so we know that opposite charges attract, similar charges repel. And so since tape and everything else really is made out of atoms, people thought, maybe atoms do have some charges. But they can't have all the same charges because not everything repels, right? So, there must be something in there that we need to look for that has some charges. And so, based on that, we said, let's look for these charges, right? So Ben Franklin, do you remember him? He was the one that proved electricity existed. And this is Michael Faraday. He's another physics guy. He suggested that atomic structure was somehow related to electricity. And we know electricity now is the flow of electrons, right? But back then, they didn't even know what electrons are and what electricity is. But from all these people, there was a link that, hey, let's look for something that has a charge, and maybe that has to do with electricity somehow. And so that led to the discovery of the electron. J.J. Thomson, one of my favorite people, there he is, was the person who discovered the electron. And this was made by one of my former students. This is J.J. Thomson here. He made this in ceramics. This was his final project. At the end of the year, we typically have a final project where you do something creative that has to do with chemistry. So inside of his head, there's a bunch of little facts about J.J. Thomson. So keep him here for inspiration. So J.J. Thomson discovered the electron, and he used something called a cathode ray tube, which is right here. So what is a cathode ray tube? So basically, it is a tube that looks like this. This is a glass tube. And what he did was he, excuse me, he hooked this up from here to a vacuum. So here's that part connected to a vacuum pump. A vacuum pump removes the gas particles, the air particles from inside. And instead of air, he filled it with a noble gas. He tried it with helium or neon. So this tube is actually filled with neon gas inside. And then he sealed this. So he removed the air, put neon in, and sealed it. And he connected it to a power source. So I have here a power source that I'm going to put this in. And so in the picture, there's your power source right here. And when we turn on the electricity, we see that there's a light, there's a beam of light. Now, neon is a colorless gas. As you can see, there's nothing in, it looks like there's nothing in there, but there is neon gas inside. It is a colorless gas. But when we hook it up to electricity, somehow we get a beam of light, right? You've all seen neon signs. When they're hooked up to electricity, they make a beam of light. And neon gives off a red colored light. If you see signs that have different colors, they either have different gases in them. Each gas will give you a different color, or the glass itself is colored. But neon will give you a red light. So he saw this beam of light. But he noticed that beam of light always bent towards the negative plate, the anode, towards the positive plate, and away from the negative plate. So when you, how like when you have a battery, you have the anode and the cathode are two electrodes. One is positive, one is negative. So because he's connecting it to a power source here, and he had two metal plates, one of them was positively charged and the other one was negatively charged because of the power source. And so he saw that the beam of light always bent towards the positive and away from the negative. And so what does he conclude based on that? Well, he concludes that whatever's in that beam of light has to be negatively charged because it's attracted to the positive plate and repelled from the negative plate. So he found that the rays bent towards a positive charge and bent away from the negative plate. Here's another picture of what he saw. So this is not neon, this is a different gas. But you can see that there is the positive metal plate, there's the negative metal plate, and the beam of light is moving towards the positive and away from the negative. And so he concluded, again, that these rays, that light has some negatively charged particles, and he called those particles electrons after the Greek word electron, meaning amber. Remember, amber is like the dried up tree sap, right? And so if you rub amber, you get like a lot of static. And so things attract and stuff like that. And so that's because of electrons jumping back and forth. And so he called whatever particles are in that light electrons. And that was the detection of the electrons. So here are some other pictures of cathode ray tubes. And old TVs and computer monitors are actually cathode ray tubes. So I have a really old TV here. I'm going to turn it on. It doesn't really have signal, just because it's analog. Now we all have digital signal. You can kind of see it a little bit here. And what I'm going to do is I'm going to take a very, very big magnet that I borrowed from the physics department. And the magnet has two ends, right? Positive and negative ends. And so if I put it here, see how I'm twisting those rays? So we're seeing that image because those are cathode ray tube. It's a cathode ray tube. Basically, these are the beams of the electrons, just like we saw with my spec tube here. So there's just a bunch of them here. And so I can twist them because we see that light from electrons, and the electrons bend towards the positive and away from the negative in my magnet. So I can bend my image. All right, so that was J.J. Thomson with the discovery of the electron. Robert Millikan was an American scientist who, here's a picture of him, who calculated the mass and the charge of the electron. And he determined that using the oil drop experiments. So there's a couple of experiments that you need to remember. The first one is J.J. Thomson's discovery of the electron using the cathode ray tube. So cathode ray tube is number one. You need to know the experiment, the name of it, who did it, what did they discover, and how. And also sketch it, be able to sketch it. So Robert Millikan came up with the oil drop experiment. This is the second experiment that you need to remember for the test. And again, he determined the mass and the charge of the electron from the oil drop experiment. So here's a diagram of what he did. So what he did was he got an atomizer, basically like kind of like a spray bottle, and he put some oil in it. And he had this big chamber here, and he sprayed some oil droplets through that chamber. So he also had two metal plates in the chamber, and he connected those to a power source. This is like a symbol for a battery or a power source. And so when we have a power source, again, it makes the metal plates electrodes. It makes them one positive, one negative. So this was positively charged, and this was negatively charged. So what happened here is he sprayed the oil droplets. They actually went through an X-ray that added more electrons to them. And as those oil droplets were falling down because of gravity, they were falling down through this hole here into this other chamber because of gravity. Well, but they also had some electrons on them, and so they're negatively charged, and so they were attracted to the positive metal plate and repelled by the negative metal plate. So those oil droplets ended up being suspended right in the middle. He was able to adjust the voltage just right so that they are suspended right in the middle. And again, they're suspended in the middle because they want to go down because of gravity. They also want to go up because they're attracted to the positive metal plate and repelled by the negative metal plate. And so based on that, he was able to calculate the mass and the charge of those electrons. Looking at the voltage, looking at the mass, he was able to calculate the charge. So here's another picture of another diagram of what he did. So there is his spray bottle. Here are the oil droplets. There's an X-ray here to give them extra electrons. And then there are the two metal plates that are charged. The top one is positively charged. The bottom one is negatively charged. And there's the droplet suspended in the middle. And here's his actual device that he used, his actual apparatus. It's pretty incredible that he was able to do that, calculate that based, with this. He calculated the charge of an electron to be 1.60 times 10 to the negative 19th of a coulomb. That's so tiny. And that makes sense because electrons are really, really tiny. Coulombs are units of charge. The mass of an electron is 9.11 times 10 to the negative 28th of a gram. Again, electrons are very, very, very tiny. There are many electrons in an atom, and the atom is submicroscopic. So electrons are very, very small. 9 times 10 to the negative 20th, that's like 0.000, 27 zeros, and then a 9. It's very, very small. A gram is about the mass of an M&M. So imagine that you're holding an M&M in your hand thinking, oh, that's the mass of 1 gram. So this, an electron, is 0.0, 27 zeros, and then a ninth of an M&M. It's very, 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 very small. So it's incredible that he was able to calculate these numbers, using that device. You do not need to memorize these numbers. This is just to give you a perspective of how tiny those electrons are. And onward to the proton. So if there are negatively charged particles in the atom, there must also be something that's positively charged, because if everything was made up of atoms that are negatively charged, everything would repel, right? And that doesn't really happen. So they started looking for the protons because they knew that they were there. But the discovery of the proton is kind of vague. There are two people that we give them credit for protons, J.J. Thomson again, and also Eugene Goldstein. So Eugene Goldstein and J.J. Thomson discovered the protons. So what they did was they used cathode ray tubes, just like J.J. Thomson had to discover the electrons, but they had removed the electrons from them. And so when they did that, they found that the rays of light, they still got the beams of light, but they saw that the rays of light actually bent the other way. They bent towards the negative and away from the positive, and so they knew that they had detected those protons. So far we know that atoms have protons and electrons. And in order to be neutral, you have to have the same number of protons and electrons. They also did some experimentation, and they figured out that the mass of a proton is almost 2,000 times greater than the mass of the electron. It's still very, very tiny. So instead of 27 zeros, it would be 24 zeros and then a 9 of a gram. So protons are very, very small, but they are bigger than an electron. They are 1,836 times more massive than an electron. You need to memorize this number. You don't have to memorize that specific one, but just approximately, it is 2,000 times more massive than an electron. So how are these electrons and protons arranged in an atom? Well, there were some theories. The first one, of course, was J.J. Thomson coming up with a theory. He called his model the plum pudding model. In the U.S., we don't really eat plum pudding, so we don't really know what it kind of looks like. So in the U.S., we call it the cookie dough model. And basically, he said it looks like a cookie dough. So if you imagine a chocolate chip cookie, the dough itself is the protons. Protons are more massive. There's a lot. They're really big, and so the dough itself are the protons. And so all this pink is basically the protons, and they're positively charged. And then embedded in there are the chocolate chips. The chocolate chips represent the electrons, and the electrons are negatively charged. This was made by one of my former students also as a final project. So this is Thomson plum pudding model. You can just look at the lid, really. And the lid kind of looks like a cookie, right? So the white would be the protons, and then these would be the electrons. So let me show you inside. She made actually, a model of the plum pudding. So plum pudding has chunks of fruit in it, and so the purple would be your protons, and then the reds would be your electrons. So the electrons are embedded inside of the protons. That was his model. There's also Nagaoka that came up with the Saturnian model. So he said that this is a little bit closer to what we think of the atom right now, a little bit better than J.J. Thomson's plum pudding model is the Saturnian model. So Nagaoka said that the atom has a nucleus inside, has a center inside that has all the protons, the bulk of the mass, and then the electrons are kind of orbiting that nucleus, just like the rings of Saturn kind of move around Saturn. But then Ernest Rutherford came along and he conducted his gold foil experiment. So this is the third experiment that you need to know. Gold foil experiment by Rutherford. And what he did was he got a source of alpha particles, an alpha particle emitter. Alpha particles are basically radiation, nuclear radiation, that are positively charged. And then he got a piece of gold, and gold is very, very malleable. So he pounded that gold until he got a very, very thin layer of the gold, and he shot those alpha particles at the gold. So then those alpha particles went through, and then he had a detection screen here to figure out where those alpha particles are going. Because remember, they were positively charged, so he was able to detect them. And what he found is that most of these particles just went straight through with no deflection at all. There were a few, that got deflected, so they went through but at a different angle. And then there were others, again, a few, that just bounced right back at the emitter, went backwards. And so what did he conclude out of this? So if you guys are here, this is my model for the gold foil experiment. So I would hold this like that, and I'd give you some marbles, and you guys would throw the marbles at me. What do you think would happen? Well, most of the marbles go through. There are a few that hit these metal wires and get deflected and go in, and there are some that hit this and bounce back at you, but the majority of them go through. Why is that? Why would the majority of them go through? Well, because the majority of this is empty space. It's just going to go right through. And so that's what Rutherford concluded, is that the atoms are mostly empty space, and that there's only a very, very tiny, dense center in the middle that has most or the bulk of the mass. And that center, based on the angle of deflection that he saw, must be positively charged. And so he came up with his own model of the atom. So this is Rutherford's model, which says that you have a tiny, tiny, dense nucleus. I'll make my picture smaller so you can see this better. So you have a dense, very, very small nucleus that has the protons, and then the rest of the atom is mostly empty space with these tiny, tiny electrons circling around. Again, we're getting a little bit closer to what we think of as the real model of the atom. Just so you have a size scale, because this picture is not to scale at all, and any picture that you see in a textbook is not really up to scale. If the nucleus was the size of a tennis ball, so about this big, right? Size of a tennis ball, the atom would have a diameter of over 1 mile. So imagine you're standing in the freeway and you're holding a tennis ball, and that's your nucleus that has the bulk of the mass, all the protons. You look half a mile this direction, half a mile the opposite direction. That's the size of the atom. That's the diameter of the atom. So the nucleus is super, super tiny, very, very small. Or if the nucleus was the size of a quarter, the diameter would be a football field. So imagine that you're at a football game, you take a quarter, and you stand right at the 50-yard line. That's the nucleus, that's the size of the nucleus, it's that size of the quarter. And then the rest of the football field is your atom with the electrons moving around. So it is really mostly empty space because the electrons are super tiny in that huge space. So far we know that neutral atoms have an equal number of electrons and protons. So far we know protons are 2,000 times greater than the electrons. And we also have these theories of how the atom is arranged with the protons and neutrons, with the last one being Rutherford. But that didn't explain something that didn't make sense. So, there were lots of examples of this, but let's look at hydrogen and helium on the periodic table. I don't know if you can see that very well, but hydrogen is right here at the very beginning, element number 1. So that 1 there is your atomic number. It tells you the number of protons and electrons. So it has 1 proton, 1 electron. Helium is right here. It's element number 2. It has 2 protons and 2 electrons. So based on that, you would think helium is twice the mass of hydrogen. But in reality, if you look at the red number, that's the mass. This has a mass of 1 AMU, atomic mass unit. This has a mass of 4 AMUs, not 2. We would expect it to have 2, not 4. And so people were like, this doesn't add up. This doesn't make sense. There must be something else in the atom that has a significant amount of mass, but at the same time, it has to be neutral because we already accounted for the positive and negative charges. And so that led them to try to look for the neutrons. You do not need to know the history of finding the neutrons. All you need to know is James Chadwick was the person who detected the neutrons. And basically he got a source of alpha particles, and he got a beryllium plate and shot the alpha particles through. And he saw basically the beam or detected the beam of neutrons. The mass of a neutron, turns out, is about the same as the mass of a proton. Not exactly, but very, very close. Both the both the proton and the neutron are about the same mass. They're both about 1 atomic mass unit, 1 AMU. The electrons are 2,000 times less massive than either a proton or a neutron. So now that we have the neutrons, where are the neutrons in the atom? Well, from Rutherford, we knew that the bulk of the mass is in the nucleus. And so Niels Bohr then suggested that the neutrons are probably in the nucleus as well with the protons. And Niels Bohr came up with the Bohr model of the atom. So 2 things that are different now from Rutherford. The first one is that the nucleus not only has the protons, but also the neutrons in them, now that we've discovered them. The other difference is that he suggested that the electrons are in these orbits, and he called those energy shells or energy levels, and that electrons occupy these energy levels. They have these orbits, and there's a certain number of electrons that could be in each of these orbitals. So like the first energy level takes 2, the second one takes 8 electrons, and so on. Now, these are all great models, and actually there were hundreds and hundreds of scientists who came up with other models that we're just not sharing. We're sharing like the most prominent models that we've had throughout history. Right now, we don't agree with Bohr's model anymore. So each person kind of added a little bit until we came with the quantum mechanical model, also known as the wave mechanical model. So that is the model that we agree with right now. And the next chapter, we're going to talk about the quantum mechanical model. But basically, we call it the wave mechanical model because we view electrons now not just as particles. We know that they have mass and volume, so they are particles, but also as waves. What comes in waves? Energy, right? So electrons are both waves like energy, but they're also particles like matter. So that's kind of interesting. They have a dual nature. Another thing that's pretty big about the quantum mechanical model, the current model of the atom, is that yes, electrons like Bohr have a certain quantized energies. They have a certain amount of energy, so they could be in the first energy level or the second energy level or the third, not in between. But also, we don't know the path of the electron anymore. It doesn't have an exact path anymore. It's not an orbit like Bohr said. We can never find the path of the electron. We can only predict the probability of finding the electron in one area of the atom at a given time. So, one of the equations that we use if you were to take physical chemistry in college, that would be the 3rd year of chemistry in college, you would use one of Schrodinger's equations to calculate the probability of finding an electron somewhere in the atom. We would not use this here, obviously. It's a lot of calculus, but it's pretty complicated, and it's pretty cool as well. And again, we're going to talk about the quantum mechanical model or the wave mechanical model a lot more next chapter. But these couple of statements here, that's all you need to know for now. All right, I hope you guys have an awesome day.